So we're going to take a look at unit circle trig. So this is a topic that it's going to allow us to figure out certain trig functions quickly. And when you get to calculus, if you take calculus next year, knowing unit circle trig is going to be very important. Okay, having some of these angles memorized, especially ones that are multiples of 30 and 45, is going to make things go a lot smoother. And in fact, that's all that unit circle trig allows us to work with easily. All right, like in terms of memorizing. If we have angles that are not multiples of 30 or 45, that's not really what unit circle trig is designed to help you quickly do. Okay? We'll talk about angles that are not multiples later on. Yes, that was that wheel you showed me. Yep. All right. So the idea of unit circle trig is basically mapping an angle to a coordinate. That's the idea. So let's say that this angle was about, I don't know, 140 degrees from here to here. The idea is if you draw a 140 degree angle and you put the initial side on the positive x-axis, the terminal side is going to hit the edge of the circle somewhere. The goal is to figure out the coordinate that I just marked. So here's another example with like a 90. Okay, here's our circle. Here's a 90 degree angle. And the goal is going to be to figure out the coordinate where the terminal side of the angle intercepts the edge of the circle.
So these are like coordinates?
They're going to be Cartesian. We're not going to have anything necessarily with an angle, but it's going to have an x and a y value. Yeah. Once we figure out the x and the y value, those are the two numbers that we need to plug into some formulas that I'm going to give you. All right. You know what? I think I'm going to reword that. Actually, that's fine. Just for certain angles, I'm going to be a little more specific. I'm going to say multiples of 30 and 45 degrees. And yes, there is some overlap there. Like 90 is a multiple of 30 and 45. Right, so we're going to draw the angle in a unit circle, and then we're going to sketch that arc, and we're going to find the end point of that arc, which is where the terminal side of the angle hits the circle. Now, you can do this, bless you. You can do this type of trig on any circle, but we are specifically going to do a unit circle. Does anybody remember when we talked about the word unit? Unit basically is telling you the size of the circle that you're going to use. Does anybody remember what unit means? Yeah, James?
1.
1. So a unit circle is a circle with a radius of 1. Okay, do we?
It's going to be like 1 foot, 1 centimeter, 1 inch.
Yeah, it's just going to be 1 unit. Yep. Do we have to use radius of 1? No, we could use any radius. But it turns out using a radius of 1, it's going to make the formulas as simple as possible. So once you find that coordinate, what does this x and y value allow you to do? Well, it allows you to find the 6 trig functions of the angle that you drew. Okay. And when I mean angle, what angle are we talking about? We're talking about this angle right here. So the coordinate allows you to find the 6 trig functions that represent the angle you just drew. And can someone remind me, what kind of angles are we going to be using on the unit circle? Only ones that are
Positive?
We can do negative. Negative will work okay, with just a different direction of rotation. Negatives will be okay.
Multiples of 30 and 45.
Right. So they're only going to be multiples of 30 and 45.
Right.
All right. So this is going to be the first time we've ever talked about the 6 trig functions, okay, in here. Does anybody know the name of any of the 6 trig functions? Either you studied them last year or you did them in shop. Anybody know one of them? Yep.
Sine, cosine, tangent, secant, secant, cotangent. And then there's-
That's all 6, yes. Perfect. So that's all 6. Sine, cosine, tangent, secant, cosecant, and cotangent. 3 of those are used more often than others, but we are going to define all of them. Okay. All of those functions are going to be defined in terms of a coordinate. So if you've done unit circle trig before and you've heard of like opposite, adjacent, and hypotenuse, the SOHCAHTOA, that's the same idea as what we're doing. And we'll connect it with that later on. But for now, we want to think of it as a coordinate. Okay, so here are your first 3 trig functions. Every trig function that we write has a 3-letter abbreviation. Generally, it's the first 3 letters of the function name, except in one case, which I'll show you in a second. Okay, and the top one is sine, the next one's cosine, and the bottom one is tangent. So the kind of question you would eventually see with this is something like this. Okay, we're not going to answer that yet, but that's what we're getting towards. Find the sine of 90 degrees. Okay, the first step to doing that is figuring out what is the coordinate for 90 degrees on the unit circle. Okay, so that's, if you can't figure out the coordinate for your angle, you can't do unit circle trig. Then once you figure out your coordinate, you're going to plug in to one of these formulas, and which one, it just depends on what they want to know. This particular problem is interested in the sine. So once you find the coordinate of 90 degrees, I'm specifically looking for the y value in that problem. Okay, if I was asking for cosine, I'd be looking for x, and tangent would be y over x. Okay. And the last 3. Cosecant, secant, and cotangent. So I said generally the abbreviation is the first 3 letters, but you can see in cosecant they don't use the first 3 letters. Does anybody know why we don't use the first 3 letters? Yes, Waylon?
It would be the same as cosine.
Yeah, it would be the same as cosine. So we've already used COS, so they just break it up into the syllables. Cosecant. And I wrote those trig functions in a very specific pattern. If you compare that to that, it's the same connection if you compare that to that. What's the connection between the one on the left and the one on the right? Yeah?
They're reciprocals of each other.
Perfect, they're reciprocals, yep. So these are what we call reciprocal functions. Sine and cosecant are reciprocals of each other. So are cosine and secant, and so are tangent and cotangent. Okay, so those are called reciprocal functions. And later on, when we talk about identities, there's going to be a group of identities in trig called reciprocal identities. And that's what they are right there. Okay, so any questions on any 6 of those definitions? Okay. So there are 4 special angles that we talk about. These are all multiples of 30 and 45, so they fit the types of angles we're going to study. And these angles are called the quadrantal angles. The reason they're called quadrantal is because when you draw them, they all land exactly on the axes, which separate the plane into quadrants. All right. So how do we do unit circle trig? Okay, unit circle trig has 2 steps. What's the very first thing I said you need to do? You need to basically map your angle to a what? You have to figure out the angle is good, but we don't really want the angle. We need the what of the angle to be able to plug into all 6 formulas. Yeah?
The XY coordinate of the, I'm forgetting the word, but I know what I'm trying to say, but I forgot the word.
Yeah, we need the XY coordinate. We need the point that represents the angle. So that's the first step. So yeah, you have it. So find the X and Y value that corresponds to your angle. Okay, at first, especially when we're learning it, we probably have to draw them out. But eventually the goal of unit circle trig is for you to be able to kind of visualize it in your head. So like if I set a 135-degree angle, you could figure out, okay, that's in quadrant 2, and you can figure out the 2 X and Y values. Yeah?
Will we learn about Euler's formula next year?
Euler's formula.
Yeah.
In calculus, or it depends if you mean statistics or
calculus.
calc. Possibly.
Mm.
Yeah. Possibly. I would say those that take statistics next year, probably not. Okay. And then once you get your coordinate, you're going to plug that into the formula. On the test, I will ask you for 1 out of the 6 per question, but to practice today, we're gonna do all 6 for the same coordinate. Okay, just practice. Okay, so any questions on the 2 steps? Find the coordinate, plug it into the formula. All right, so let's try an example. Sometimes step 1 is already done for you. If they give you a coordinate, great. They've already done half the problem. So this coordinate is going to represent a certain angle. What angle it represents isn't really important. What's important is that we know the coordinate. But while we have it up there, does anybody think they know what angle, if you drew it on this circle, would have the terminal side go through the coordinate 0, 1? 0, 1 is on the edge of the circle somewhere. Anybody think they know the coordinate? Yeah?
90 degrees?
That's a 90-degree angle, yes. Important to the problem? No. We have the coordinate, which is what's important. Let's start to just make a diagram. The coordinate for a 90-degree angle is 0, 1. All right. So now let's do our 6 trig functions. Sine, cosine, tangent. And then can somebody tell me what's the function that's the reciprocal of sine? What do we call that one? Yep.
Cosecant.
Cosecant. Reciprocal of cosine is, anyone else remember that one? Yeah.
Secant.
Secant, perfect. And Joe, how about the reciprocal of tangent? Perfect. Okay, so really, once we get the 3 on the left and we get those answers, we just take each one of them and flip them, and that gives us the 3 on the right. Okay, so let's start with sine. Cole, what's my formula to find the sine? You don't remember? Do you have it? Do you have it in your notes? No. Can anyone help him out? Waylon, what's the formula to find the sine?
Theta equals y.
Theta equals y. Yep. So we get the y value. What's the Cole? What's the y value in the coordinate they gave us?
1.
Yeah. Perfect. Nice. So that's it. The sine is 1. Let's do the cosine. James, what's our formula for cosine?
Theta equals x.
Yep. So we get x. And what's the x value in this problem?
0.
0. Okay. Tangent. Maddie, how about my formula for tangent?
1 over 0.
Yeah, it's going to be y over x, which in this case is 1 over 0. And what do you get if you try to do 1 divided by 0? Yeah, Kim?
Undefined.
Undefined. Undefined. Yep. All right, now that we have the 3 on the left, we flip them all, and that gives us the 3 on the right. What do you get if you take the number 1 and flip it? Yep, 1. How about if you take 0 and flip it? Think of it as, if you're not sure how to flip 0, think of it as 0 over 1. That's what it is now, and you're going to flip that. Yeah. That becomes undefined. So if you flip 0, you get undefined. What about if you flip undefined? Yeah.
You should get 0.
You get 0. Perfect. So that would be 6 separate questions on the test. Those are the 6 trig functions for the coordinate 0, 1, which really represents the coordinate for 90 degrees. All right, so while we have this up, let's just see if we can figure out the coordinates for the other quadrantal angles. What do you think the coordinate would be for 0 degrees on the unit circle? Yeah.
1, 0.
1, 0, perfect. How about the coordinate for 180 degrees? What do you think that one would be?
Negative 1, 0.
-1, 0. And the angle at the bottom? Yep.
0, -1.
0, -1. And Waylon, what is that angle?
It's the 270.
It's the 270. Yep. So because it's a unit circle, each coordinate basically represents right one, up one, left one, down one from the origin. When we start going in between, like the 30s and the 45s, then the coordinates get a little more complicated. Okay, but we'll take a look at that. All right, so look at that coordinate, 1/2, comma, √3 over 2. Does that coordinate, right there, look like any of the ones we just wrote down? What do you think? Does it look like any of the ones we just wrote down? Moises, what do you think? No. Why? What's different about it? They're both fractions. Yeah, we didn't have any fractions in these other coordinates. And what else is in those coordinates that we didn't have? Yeah, we have a square root in there. Okay. So that is not the coordinate for 0, 90, 180, or 270. It is the coordinate for some other angle. Do we need to know what that angle is right now? No. Okay. Will you later? Yes. Okay, but for now, all we need to know is this coordinate represents an angle. We have the coordinate. We just have to fill it into the formula. So let's start with the sine of, and whenever you do a trig function, whatever you put right there is always an angle. We don't know what the angle is in this problem. So they told us to use theta. Once we study more about unit circle trig, you will know what angle that represents. Right? That is a, if you really want to know, that's the coordinate for a 60-degree angle. That's what it is. It's a 60. All right. So let's start with the sine. What would be the sine of the angle represented by that coordinate? Yeah. Yeah, but sine is the y value, which is root 3 over 2. We always leave the answer exact. You don't want to plug that in and say like 0.866, which is, that's what it would round off to. Don't do that. Okay, just leave it as root 3 over 2. How about the cosine of the angle represented by that location? Yeah. 1/2. That one would be okay if you put 0.5. Why do you think I'd be okay with a decimal on that one, but not the one above it?
Because it's not irrational like the above one.
Right, it's not irrational. It's a decimal that stops. 1/2 is exactly 0.5. Okay. Now, tangent. When we do tangent is a fraction. Can somebody remind me what goes on top for tangent? Yeah, Holly? Y, and then what goes on the bottom? X, perfect. So y on the top, x on the bottom. And I'm doing this off to the side because we have a little bit of work to do. We can't leave our answer like that, because we have a fraction over a fraction. When you divide two fractions that have the same denominator, or when you divide any two fractions, normally you would take the bottom one, you would flip it and multiply by the top. But if you take that bottom one and flip it and put it in the top, what's going to cancel out? Yeah. Nope, not sure. Anyone think they know what's going to cancel out? Yeah, Ben?
The twos.
The twos, yeah. So when we see two fractions with the same denominator, we can just cancel the twos right away. And Ben, can you tell me what's left there?
They're squared over 1.
Can you say that one more time?
3 squared over 1.
Square root of 3, sorry.
Yeah, square root of 3 over 1. Perfect. And that's it. All right, so you do, when you get a trig function that has a fraction over a fraction, we do have to simplify as much as we can. Okay, bless you. Any questions on how we simplified that? Okay. Now that we have the three answers on the left, can someone remind me, what do we do to those three to get the other three? Take each one of them and flip them. Yep. So we're going to have the cosecant, secant, and cotangent. All right, let's start with the secant. That's the easiest one to flip. What do you get if you flip 1/2? Cool?
2.
Perfect. You get 2. All right. The cosecant. That one, when we flip it, we're going to have to do two things. You're welcome.
Bye, everybody. Bye-bye. I don't understand one thing he said.
Oh, that's not good. Maybe it's me.
No.
Oh.
It's 1,000% me.
Okay.
You know that. I took one day of honors math in high school and was like, no, goodbye. Do you have a second?
Sure.
So Miss Trundy and I went to high school together. Did you guys know?
All right. So when we flip the sign, what's the first thing that happens? We don't have to fix it yet, but just tell me the first thing that would happen. Because we're trying to get the cosecant. So we're going to flip the sign. Yeah.
2 over the square root of 3.
All right. So we can start with 2 over the square root of 3, but we can't leave it like that. Why not? What's wrong? Yeah.
You can't have a square root of the bottom.
Right, we can't leave that square root in the bottom. So how do we rationalize or fix having the square root in the bottom? Remember what you multiply by to do that? Yeah?
Would you multiply it by the square root?
Yeah, so multiply by the square root of 3 over We can't multiply by the square root of 3 over 1 because that would change the problem. You
Square
can,
root of 3 over square root of 3.
right, you can only multiply by the same thing in the top and the bottom, which is effectively multiplying it by 1, but in a way that makes something special happen. Okay, in the top, we get 2 square roots of 3, and in the bottom, what do we get?
3.
3. Okay, in the bottom, you get square root of 9 or 3. Okay, so the cosecant is 2 root 3 over 3. And let's do the cotangent. All right, what would be my first step to get the cotangent before I fix anything?
Would it be the first step putting 1/2 over 3 square roots of 2? It's x over y.
So how are we getting the cotangent? What are we doing based on the work we already have? We can do the cotangent a little faster.
It's the opposite of the tangent.
It's the what of the tangent?
Reciprocal of the tangent.
Reciprocal of the tangent. Yep.
So it'd be 1 over the square root of 3, which we then do the same process again,
Mhm.
which would then make it just the square root of 3.
No, it wouldn't be the square root.
of 3 over 3.
Yeah, square root of 3 over 3. Yep. And that's your final answer. All right, and that's the 6 trig functions for the angle represented by that coordinate, which I told you the angle was 60 degrees, but you don't need to know that yet. Okay, any questions on those? All right. So now let's try the 6 trig functions of 90 degrees. Okay, what's different about this question compared to the last two? Yeah,
It gave you an angle, not a coordinate.
right. They gave me an angle, not a coordinate. That's fine, but I can't work with 90 degrees. To do unit circle trig, I need to map that to a coordinate. So now this is where we want to kind of think in our head. Imagine the circle. Imagine 90 degrees on the circle and figure out the coordinate. Okay, what's the coordinate for 90 degrees? Win?
0.
Right, points right here. That's 0, 1, and we already did that question. So now, once you figure out the coordinate, this is the same as example, was it 1A? That was the only extra step. So any question on how you would now plug those numbers in and do what we did right there? Okay. Does anyone need me to write them all down again? The only difference in how you write your answers this time is you actually know what to put there. Okay? It's supposed to be an angle. It's kind of like when you write log and then you fill something in. That's exactly what this is. That is the argument to the function. It's what you're plugging into it. When you don't know what you're plugging in, usually you just put a theta. When you do know what you're plugging in, you can fill in the actual angle. Right, let's try this one. Find the 6 trig functions of 270 degrees. Okay, and this one we'll do because we hadn't gone through these. All right, what's before we can start using the formulas, what's the first thing we need to figure out? Yeah.
Coordinate.
Right, we've got to figure out what coordinate 270 degrees is represented by. So ideally, if we can do that in our head, that's kind of what we want here. So imagine the circle, picture where 270 is, and then tell me the coordinate to get to 270 degrees. Wait.
0, -1.
0, -1. So it is similar to 90, right? It has a 0, it has the 1, well this is a -1. So you're going to get all the kind of similar answers. You'll get some 1s, or some -1s, some 0s, and some undefineds. But they might be in different spots. All right, so let's do sine of 270. Nick, what's the sine of 270?
-1.
-1. Holly, how about the cosine of 270?
0.
That is 0. And the tangent of 270? How about, yeah, Lucas?
Undefined.
That's undefined. The tangent is when you take the 2 you have right above it, and just imagine putting a division sign there. It's y divided by x. Whenever you divide by 0, undefined. Now flip them all, and those are the next 3. So Michael, what's my cosecant going to be?
1 over -1.
And what will that reduce to?
Negative, or yeah, -1.
Yep, -1. Good. Okay, how about the secant? Kaylee, what's the secant of 270? Undefined, because think of it as 1 over or 0 over 1. When you flip that, 0 goes to the bottom. So undefined. The quadrantal angles are the only trig functions that can ever have the secant. Let me think, is that actually true? Tangent and cotangent has some undefined values too. But, yeah, and so does secant. Well, I'll say it this way. Sine and cosine will never be undefined. Okay? You can get an undefined in the other 4 spots. Secant, cosecant, tangent, and cotangent. But you cannot get undefined in these 2 spots. Ever. It doesn't happen.
Because they have no global maximum or global minimum.
Yeah, so we're going to talk more about the graphs later, and that'll kind of give you a hint at why these will never be undefined. But for now, just know that they are not undefined. How about the cotangent? Yeah, Ryan?
0.
That's going to be 0. And notice, it's not like -1 degrees or -1 radians. The answer is not a degree or a radian. The answer is just a number that does not have a label attached to it. The degrees or the radians come in here. It's what you plugged into the function to get that answer. And what I'm pointing to can be either a degree or it could be a radian. So this says find the 6 trig functions of pi. How do you know that what you're plugging into the trig function this time is radians and not degrees? It doesn't have the degree symbol. Okay, whatever you put in right here always has to be an angle. That's how trig functions work. You're always plugging an angle into the types of trig functions I gave you today, whether it's degrees or radians. So they gave me an angle. What is it that I need to figure out about that angle? Yep.
You guys trying to do radians to degrees, right? That's a symbol radians.
Not technically. What is it that I need to figure out? So that's a little bit different question. Maybe not how I figure it out, just what do I need to know? Yep.
The coordinate on the answer.
I need the coordinate. That's all I need. If you can figure out that coordinate without using degrees, that's even better. If you have to go from radians to degrees first, you can do that. It's going to slow you down a little bit, but it's okay if you need to do that for now. So does anybody think they know what the coordinate is for pi radians? I'll give you a hint. We know 2 pi is all the way around the circle. So pi is halfway around. Yep.
20 is degrees.
And what's the
So it would
coordinate?
be -1, 0.
Yep. Coordinate is -1, 0. Okay, that is 180 degrees, but ultimately I need the -1, 0. All right, and we haven't done, I know we've done one similar, but let's fill this in because they are going to be a little different. Basically different spots. Okay. What is my sine going to be? Yep.
Sine is going to be 0.
Sine is 0. Okay, Jack, how about the cosine?
-1.
-1. Moises, how about the tangent? That's going to be 0. Yep, because it's 0 divided by -1. And Aiden, what am I going to do with those 3 on the left to get the 3 on the right?
So for sine, you can do the inverse, and then for all of them, you do the inverse. For the reciprocal.
Reciprocal, yeah. So just take the 3 on the left and flip them. So undefined, -1, undefined. Notice when it's -1 and you flip it, it stays the same. There's only 2 numbers you can flip in math and they stay the same. -1 is one of them. What's the other one? Yep.
1.
Yep. Negative and positive 1. All right. So any questions on the 6 trig functions there? All right, let's try this one. Find the 6 trig functions of 7 pi over 2. All right, not as easy of a radian to work with, so what might you want to do this time to help you? Yep.
Convert to degrees.
Right.
Make it easier.
You can convert it to degrees. So you multiply by 180 and divide by pi. So it's going to end up being 7 times 180 divided by 2. So that is 630 degrees. Okay, so we converted it to degrees, but I'm still not crazy about that either. What do you think I don't like about 630 degrees? Yeah.
It's more than 360.
Right, it's more than 360. Okay, I would rather work with an angle that is smaller than 630. Does anybody know what you can do to make that angle smaller? Yeah? Subtract 360. And what do we call that new angle right there, 270? 270 is something with the original. Yeah? It's coterminal. The terminal sides end up at the same spot. So now that's 270. And 270 degrees, we've already done that problem. So that was example 3. So is there any question on how we got it to 270? Because then from there, we've already done the problem. All right. Let's look at this one. -90. Again, not an angle that I prefer to work with. What can I do to -90 to fix that so it's not negative? Yeah. Add 360, and that'll give me how much?
270.
270. That's the same question again. So there's lots of ways I can ask questions that they look a little different, but they end up actually being the same problem. So 270 degrees, same as example 5, which is the same as example 3. From there.
So what you're telling me is this could be very repetitive.
Well, when you're dealing with just the quadrantal angles, yeah, there's not a lot of variety because you're only dealing with, in terms of coordinates, you're only dealing with 3 numbers, a 1, a -1, and a 0.
There's the 4 major angles and then there's 12 minor angles. Which
Yeah.
is like 30, or 30, 45, and 60.
And that's
3.
part of what we're going to start but not finish today. We're going to talk about the 45 and the 30. Yeah. So it's the last part of section 6.2. Okay, so the last thing we're going to look at for this week, still 6.2. It's just a little bit more with unit circle, looking at angles that are not necessarily 30s, are not necessarily quadrantal. Just to make sure we know which ones are which. How much is pi over 6 in degrees? Yeah?
30 degrees.
That's your 30. Pi over 3?
60.
That's your 60. And pi over 4?
45.
45. So if we can get through just talking about these 3, then we can talk about multiples of them tomorrow. Multiples are easy to do once you know how to do the basic ones. And we might talk a little bit about trig identities. It comes up in this section. We spend a whole, like, maybe 3 days on it later on. But it comes up a little bit in this section because of the reciprocal identities, which I've already shown you. How you can flip one trig function to get the other. That's why you don't have buttons on the calculator for secant, cosecant, and cotangent. You only have sine, cosine, and tangent because you don't need the other ones. All you have to do is take the one that has a button for it and flip it. And no, it's not the same as pressing second sine. What I just put on the board, that is not sine flipped.
That is arc sine.
Yeah, that's arc sine, which we're not going to talk about this week. So I know it's kind of weird, but what I just wrote there and what I'm writing
Inverse.
here, those are not the same thing. Okay, I know they both have a -1 as a power, and it's a little weird they use this notation, but normally -1 does mean to flip it. And with the one on the right, it does. That means to flip sine and get the cosecant. But the one on the left, that's a totally different thing. It's just a notation thing we need to talk about, but not right now. Okay, so the point is, there is no button for inverse sine, there is no button for secant, cosecant, and cotangent. Just take the ones you have and you flip them. All right, so let's take a look at a 45-degree angle. If we're going to try to do unit circle trig with a 45-degree angle, what is it that I need to know about a 45-degree angle? I need to know the
point.
The point, yep.
Which is square root of 2 over 2, square root of 2 over 2.
Yes, and that's what we're gonna come up with right now, just in case everybody doesn't know how to get it. So a 45-degree angle, basically it's halfway between 0 and 90. What I generally do is think of it as a triangle. That black ray is your hypotenuse. Draw a dotted line straight down and make a 90. What kind of triangle did I just draw right there?
Right.
Okay, it is a right triangle. Can you be a little bit more specific?
45, 45, 90.
Yep, so this is a 45, this is a 45, that's a 90. And because I have two angles that are the same, it makes that a, yeah? Right, it's an isosceles triangle. And we can use that to help us figure out this side and that side. So now I've taken that triangle that I had up there and I drew exactly the same diagram, just a little bit bigger down here. The hypotenuse I already know. How long is the hypotenuse
1.
in that triangle? Yeah, it's 1 because it's the radius of the circle. Now, I don't know what these other two sides are, but how does the base and the height compare to each other? They're equal. So we don't know what they are, so we're going to pick a variable, but don't pick two variables, pick one, because they're the same. It doesn't matter which letter you use, but pick a variable and use that to represent both sides. If these angles were different, then all the sides would be different, and we couldn't do what we just did right there. All right, so basically now I need an equation I can set up involving the sides in a right triangle, because I'm trying to solve for x. Once I know what x is, that's going to tell me if that's the origin of my unit circle. That's going to tell me how far right to go once I know x. And x is also going to tell me how far up to go to get to that point right there, which is that point right there. So that's what I'm trying to figure out. How far over, how far up. So I'm going to find the lengths of those bold sides. Does anybody remember a theorem you can use to find the lengths of the sides in a triangle? Yeah. Yeah. And what is the Pythagorean theorem? Yeah.
A squared plus b squared equals c squared.
Okay, can you explain that? Because I don't have any A, B's, and C's up there, so I'm not sure what you mean by A's, B's, and C's.
C is the hypotenuse.
Okay.
And A and B are the legs.
A and B are the legs. So we're going to fill in leg squared plus leg squared equals hypotenuse squared. So leg squared, hypotenuse squared. What's x squared plus x squared? Yeah,
2x squared.
2x squared. And now get x by itself. So divide by 2. X squared equals a half. But I want x, not x squared. So how do I get rid of that exponent of 2 on the x? Yeah,
Square root of.
square root it. And when you take the square root of a fraction, you do the top and the bottom separate. Okay. What's the square root of 1? Square root of 1 is, yep, 1. But we can't leave that like that. How is 1 divided by the square root of 2 going to look once we fix it so there isn't a square root in the bottom? Yeah.
Is it square root of 2 over 2?
Yes, it's going to be square root of 2 over 2. So that is the length of the bottom side of that triangle. Square root of 2 over 2. What's the height of the triangle?
Square root of 2 over 2.
It's also square root of 2 over 2. So now we know the base. We know the height. So what's the coordinate to get to 45 degrees?
Square root of 2 over 2, square root of 2 over 2.
Square root of 2 over 2, comma, square root of 2 over 2. And that is always the coordinate for a 45-degree angle. It absolutely has to be memorized. Square root of 2 over 2, comma, square root of 2 over 2. You do not want to have to go back and figure that out like we just did every time. And once you know how to do the 45-degree angle in quadrant 1, because you know the coordinate, doing a 45-degree angle in quadrant 2 isn't bad at all, because it's just this triangle reflected. So every 45-degree angle ends up being root 2 over 2 and a root 2 over 2. It's just a matter of, are they both positive? Are they both negative? Or is one negative and one positive? Right? But once you know the coordinate in quadrant 1, you know the coordinate for a 45 in every quadrant. Okay, so that's the coordinate for a 45-degree angle. Any question on that one? Okay. Let's practice an example of that. I'm going to save the 30, 60, 90 for tomorrow. So we have to figure out the coordinates eventually for this triangle. But this triangle is a little bit harder because what's different about it?
Not all angles are the same.
Not all angles are the same. So what does that mean?
It's 3 values.
Right, the sides are 3 different values. So you can't use the same trick with Pythagorean theorem right away because you don't know 2 sides. Okay? And they're different. That's what makes it a little harder. All right. So this says find the 6 trig functions of 45 degrees. So the questions in this section are the same type of question that we already saw. It's just the number that you're putting here might not be a 0, 90, 180, or 270 anymore. All right. What's the first thing that I need to know in order to do unit circle trig?
The coordinates of the point on the arc.
I need to know the coordinates, yes, of where that terminal side of a 45-degree angle would hit the circle. How are we going to figure out the coordinates for a 45-degree angle?
Square root of 2 over 2. Isn't that the one? Yeah.
How do you know that?
Pythagorean theorem. most.
Okay, without going through Pythagorean theorem again, how do we know that's the coordinate? Where are we going to normally get that value for the coordinate from now, going forward? Yep?
I think it's like the previous problem.
Right, but I don't want to go through that anymore. So from now on, we're going to get the coordinate by,
Using the circle.
yep,
You just remember it.
you're going to remember it. You're going to remember that coordinate. Okay, we're going to have to memorize that that is the coordinate for 45 degrees. That's where it's going to come from. So root 2 over 2, comma, root 2 over 2. Okay, so let's start with the sine. How about, Ben, what's going to be the sine of 45 degrees?
Would the sine of 45 degrees just be root 2 over 2?
Yeah, and since they're both root 2 over 2, can you just tell me which one you picked, the x or the y?
Would that be the 1?
It would be which one?
The 1.
The 1?
The y.
Oh, the y, yeah, thanks. The y. Okay, so the y value, even if you switched them, you'd get lucky in this problem because they're the same, but normally you can't switch them. You gotta remember which one is which. How about cosine of 45? What's that going to be? Yeah, right.
It'd be the same thing, but just the x instead.
Right, it's going to be the same thing because the x and the y are the same, but specifically it is the x. Okay, and how about the tangent? If you take the y and divide by the x. Yep,
Because it's the same, the tangent's going to be 1.
right. We're dividing two things that are the same, so we're going to get 1. So we can quickly do the cotangent. What's the cotangent of 45 going to be? Yeah.
1 as well.
It's also going to be 1. Now, these are going to take just a little bit longer, but once we get one of them, we know the other one. Okay, what's going to be the first step to finding the cosecant of 45? Top one. Yep.
You flip it over to get the reciprocal, so it would be 2 over the square root of 2.
So we're going to flip the sign, but don't leave it like that because you get the
Yeah.
root in the bottom.
So then you gotta multiply it by square root of 2 divided by square root of 2, which then gets you 2 square root of 2 over the square over 2, which 2 and 2 cancel out, so you just have square root of 2.
Yeah. And eventually that's something we want to memorize too. Okay, if you're going to work with this a lot, doing all this stuff that just cancels out, it's easy to, if we can just remember, when you flip root 2 over 2, you get root 2. All right? So when you flip root 2 over 2 here, what are you going to get? Kim? Square root of 2. I mean, it's not the end of the world if you have to keep doing it out. I will tell you, it's going to slow you down in calculus, and it's going to make some things harder. So it's good to start to memorize some of these values. Okay, and that's how you do the 6 trig functions of 45 degrees. Any question on that one? Okay. I don't want to go through the whole problem. I just want to see if you could tell me the coordinate. What's the 45-degree angle in quadrant 3? How much is it? Yeah?
Would it be negative root 2 over 2 and root 2 over 2?
Yes, that's the coordinate, but what's the angle going to be?
45.
45 is in quadrant 1.
225.
Yep. So if you see a problem that asks you about a 225-degree angle, that is a multiple of 45. Okay. 45, 135, 225, 315. Those are your 45s. And then, as Waylon just said, the coordinate has both root 2 over 2s. They're just
One has a
negative.
square root, not both.
Oh, thanks. I like square roots, that's why I'm writing it. So now you end up doing the same problem we just did, except x and y are negative. Right? But the arithmetic is going to be the same level of difficulty. All right. So that's more of what we'll focus on tomorrow. Okay, we'll focus on doing the 45s and other quadrants, and then I'll show you how to do the 30s and the 60s. We didn't do those at all. Okay. So for homework, we already did page 324. So on page 335, I want you to do 1, 5, and 8, which I think 1, 5, and 8 ask you to find the coordinate. But then I also want you to use the coordinate to find the 6 trig functions. So you should have 6 answers for every problem in tonight's homework. Sine, cosine, tangent, secant, cosecant, cotangent. So 1, 5, and 8 are in the book. And I'm just going to add one more onto that. So do 1, 5, and 8, find the 6 trig functions. And I'm giving you 3 other problems that are angles. I want you to find the 6 trig functions of those. But since I gave you angles, you're going to have to do something with the angles first. And then I'm also giving you a coordinate that I want you to try to find the 6 trig functions of. That one's easier because you don't have to figure out the coordinate. You already have it. So just don't forget about the 405 down here too.